Morning students, welcome to our online video class of chemistry. In previous class we had discussed about black body radiations and also about Planck's quantum theory. Did you remember what is Planck's quantum theory? The energy distribution in black body could not explain on the basis of application of classical physics. And the correct expression for that was discovered by Planck by using quantum theory of radiation. And the theory are: the radiant energy is absorbed or emitted is not continuously but discontinuously in the form of small discrete packets, that is called quanta. Small discrete packets of energy is called quanta. Then each quantum is associated with a definite amount of energy equal to h nu, where h is called a constant, that is Planck's constant, and the numerical value of h, Planck's constant, is 6.626 into 10 to the power of minus 34 joule seconds. And here nu is the frequency of the radiation emitted or absorbed. The amount of energy associated with a quantum of radiation is proportional to the frequency of radiation, that is E is proportional to nu equal h nu, where nu is c by lambda, where c is the velocity of light and lambda is the wavelength. Here the energy associated with a quantum of radiation depends inversely on its wavelength. Therefore, E equal hc by lambda. The energy emitted or absorbed by a body is always an integral multiple of the basic unit quantum equal to h nu. That is, if energy of body changes from a value E1 to a value E2 by emission or absorption of radiation of frequency nu, then E2 minus E1 equal to nh nu. That means a body can emit or absorb energy only in whole number multiples of quantum, that is 1h nu, 2h nu, 3h nu, nh nu. Planck, however, did not explain why energies should be quantized. However, with this assumption, he could explain the distribution of intensity of radiation from a black body as a function of frequency at different temperatures. Now we are going to discuss about photoelectric effect. The photoelectric effect was discovered by Hertz in 1887, and he observed that when a beam of light of suitable wavelength falls on a clean metallic surface or clean metallic plate such as cesium, rubidium, potassium, electrons are emitted from the surface of the metal plate. This phenomena involving the emission of electrons from the surface of metal by the action of light is called photoelectric effect. And the electrons so emitted are known as photoelectrons. In definition, photoelectric effect is the phenomena of ejection of electrons by certain metals like potassium, rubidium and cesium, etc. when light of suitable frequency incident on them. The experimental setup for the photoelectric effect is shown in this figure. It consists of a evocator chamber and it is coated with the a photosensitive metallic surface, that is cathode, and it is connected with the negative terminal of the battery. Then a detector is connected with the emitter. It is then connected with the positive terminal of the battery. When light of suitable frequency is allowed to fall on the cathode, then the electrons are emitted from the metallic surface. These electrons then travels towards the positive charge detector. This causes a continuous flow of electrons through the circuit, and the electron flow through the circuit can be measured by ammeter. The important characteristics of photoelectric effect on the basis of experimental observations are: the electrons are ejected from the metal surface as soon as the beam of light striking the surface. That is, there is no time lag between the striking of light beam and the ejection of electrons from the metal surface. That means there is only little time lag between the light striking the metal surface and the emission of electrons. Next characteristic is the number of electrons ejected is proportional to the intensity or brightness of light. That means the number of electrons emitted per unit time depends upon the intensity, not on the frequency of the radiation. And during the experiment, it is observed that the light striking on the surface of metal is not able to cause the ejection of electrons or photoelectrons, as they are called, if it does not have a certain minimum frequency, irrespective of what is its intensity is. The maximum frequency of light required to eject photoelectrons from a metal is known as threshold frequency. That means electrons are emitted from a metal surface only when the frequency nu of the incident radiation exceeds a certain characteristic value. This frequency is called the threshold frequency nu zero. The value of nu zero depends upon the nature of metal used. Next one is the kinetic energy of the ejected electron is directly proportional to the frequency of the incident light. We study that the kinetic energy of photoelectrons are proportional to the frequency of incident light, and this is shown by the linear graph A. And the figure B shows the plot of kinetic energy of photoelectrons versus intensity of light. Kinetic energy is independent of the intensity of incident light. Any increase in the intensity merely increases the number of ejected electrons. Discuss some characteristics of photoelectric effect based on the experimental observations. And the above observation cannot be explained on the basis of wave theory of light, because according to it, a more intense beam should expel electrons with the higher kinetic energies, which does not happen actually. The phenomena of photoelectric effect and the related observation can be explained if light is treated as having particle nature. So, therefore, the classical physics failed to explain photoelectric effect. In 1905, Einstein was able to explain photoelectric effect using Planck's quantum theory of electromagnetic radiation. We have studied that according to Planck's radiation, light may be regarded as a stream of particles, that is called a photons. Then he observed that when a photon of frequency nu, which is greater than threshold frequency nu 0, strikes on the metal surface. If nu is greater than nu 0, then the excess electrons is imported to the electron has kinetic energy. Greater the energy possessed by the photons, greater will be the transfer of energy to the electrons, and greater the kinetic energy of the ejected electrons. What is kinetic energy? It is half mv square. Kinetic energy of electrons is directly proportional to frequency of electromagnetic radiation. And the minimum energy required to eject the electrons is h nu 0, so called work function W0. When a photon of frequency nu, which is greater than the threshold frequency nu 0, strikes an electron in a metal, it imparts its energy, that is h nu, to the electrons. Of this, a portion called photoelectric work function, which is represented by W0, enables the electrons to overcome the attractive pull of the nucleus and to break away from the atom. Then the difference in kinetic energy, h nu minus h nu 0, is transferred as kinetic energy. Then the kinetic energy of the ejected electrons, that is half mv square, would be equal to h nu minus h nu 0. Also we can write it as half mv square equal h nu minus h nu 0, or h into nu minus nu 0. Equation is called the Einstein photoelectric equation. We can write this equation as h nu equal h nu 0 plus half mv square, where me is the mass of the electron and v is the velocity associated with the ejected electron. And a more intense beam of light contains larger number of photons, so the number of electrons ejected is also large. Photoelectric effect finds application in the functioning of photoelectric cells used in photoelectric colorimeters and spectrophotometers and photographic light meters and also street light controllers, etc.